A useful application of partial pressures arises when you collect gases over water. Basically, a gas displaces water in an amount equal to the volume of the gas. The volume of the gas is equal to the volume of the water collected. As gases bubble through the water, the gas becomes saturated with water vapor, meaning that you must account for the water vapor pressure in the measured pressure. Partial pressure of the water in this mixture depends only on the temperature. So the vapor pressure of the water can be looked up very easily in reference books at the particular temperature that your experiment is being run. Look at an example. Suppose a 156 milliliter sample of hydrogen gas was collected over water at 19 degrees C in 769 millimeters of mercury. What is the mass of the H2 collected? Well, first we must determine the partial pressure of the hydrogen gas, since the total pressure involves water vapor. At 769 millimeters of mercury involves the water vapor pressure as well as the hydrogen gas pressure. Note that the water vapor pressure can be obtained from the water vapor pressure tables and reference books that are at the correct temperature, which in this case is 19 degrees C. So I looked up the vapor pressure of water at 19 degrees C, which is 16.5 millimeters of mercury, on a test that would be given to you. Well, we know the total pressure is equal to your pressure of your hydrogen gas, which is important to us, plus your pressure of your water vapor. So what we're going to do here is rearrange this. Since we know the total pressure and we know the vapor pressure, we can subtract the vapor pressure from both sides and solve for our partial pressure of hydrogen gas. So that means partial pressure of hydrogen gas is equal to your total pressure minus your vapor pressure, which is 769 millimeters of mercury, minus the 16.5 millimeters, which came from reference books, which gives me 752 millimeters of mercury. That is the partial pressure of our hydrogen gas. So now we can go plug that into the ideal gas law and solve for our number of moles and go on from that to get our mass. Next, we can determine the moles of gas through the ideal gas law. Partial pressure of hydrogen gas times volume is equal to the number of moles of hydrogen gas times RT, by using the partial pressure of the hydrogen gas we just calculated, and the volume of the water displaced. That's how we determine how much gas was there by the amount of water that was collected, since it equals the volume of the hydrogen gas generated. We also need to make some conversions of the units to get things to cancel out. So, your number of moles of hydrogen gas equals your partial pressure of hydrogen gas times volume divided by RT. So we know 752 millimeters of mercury, our partial gas. We also need to convert that into atmospheres. So we got 1 atmosphere is 760 millimeters of mercury. We also know the volume of the hydrogen gas was 156 milliliters. That's equivalent to the water collected. But we're going to have to change that to liters to get them to cancel. So we got 1 liter is 1,000 milliliters. Then we also have the ideal gas constant, which is 0.0821 liter atmospheres per mole Kelvin. And we have 19 degrees C, but we got to change that into Kelvin, which is 292 Kelvin. Units cancel. You can see what's left is moles, which is in the denominator of the denominator, therefore it's in the numerator. So if I calculate my numbers, I get 0.00644 moles of H2. Lastly, we need to convert moles to mass. That's just going through molar mass. So I got 0.00644 moles of H2, molar mass of H2, 2.02 grams of H2 per every 1 mole. Units cancel. All I have is grams here, which is what I'm looking for, which tells me I got 0.0130 grams of H2. Homework 47 and 48.